like I said, take a look at both of those. See if you can do those. See if you can just evaluate those. Remember, I told you once we get to the test in a couple of weeks, day 1 of the test will be a no calculator day, so you'll see things like this. Day 2 of the test will then be problems where you would actually need a calculator to solve. Okay, so these types of things you need to be able to do in your head. Okay, and I tell you that now so that you can be practicing that and doing that as you work your way through it. Let's see what you got. What's number 1? What's the answer? 3. Very good. What this is really asking you is, when we say log base 4 of 64, this is really saying 4 to what power gives you 64? What's the power that I'm going to raise the base to? Well, 4 squared is 16. Multiply by another 4, you end up with 64. Your answer here is 3. Okay? Log base 4 of 64. How about number 2? This one should be quick now that we went over problem 41. It's the same thing as what we just did. -1. Okay? This is saying a raised to what power gives me 1 over a? Well, when it gets dropped into the denominator, that's that -1 as an exponent again. Okay? That's that -1. Similar to like what we just did, like I said, on problem 41 from your assignment, where you had the 2 and the 1/2 being a power of -1. Okay? So just a quick refresher. Like I said, we'll keep working on those, keep making sure you can do those. Here's where we are headed today, like I told you. Section 3.2. We started the chapter by looking at graphs of exponential functions, exponential growth, exponential decay, and then doing all the shifts and stuff. We're going to do the same thing now, but now with logarithmic graphs. Okay? And we're going to relate it back to that. Most of the process, though, is going to be the same. Very, very same process. All right, so here we go. First off, quick review of graphs. Let's go back, and you don't necessarily have to write this down because you should already have it in your notes from your exponential functions, back to last Friday. Just a reminder, when you have an exponential function, and it's right over there on the wall, okay? There's your parent function right there. That's the one we're talking about. We start off with a Y-intercept at 1. Our domain is all real numbers. I can take anything and raise it to any power I want. Positive, negative, 0, fractions, decimals, doesn't matter. The range, remember there is a horizontal asymptote at y equals 0, which makes the range from 0 to infinity. Okay? Puts it above that graph. It's an increasing function, assuming we're going to mainly look at logarithmic growth. We're not going to look too much at logarithmic decay. And therefore, we're going to kind of focus on exponential growth. So increasing and continuous, and we kind of already talked about y equals 0 is where your asymptote was. We'll then get into the idea of what happens. Let's go back now. I told you yesterday at the beginning of the hour, the first thing I said was, when we're looking at logarithms, the number one thing I started with was that logarithms are just inverses of exponentials. Think back to chapter 2 when we were finding inverse functions and all that kind of stuff. We flipped something. What was it? When we were finding inverse equations, when we were finding domain and range, what did we flip? Remember? You flipped the x and the y's. Okay, if you remember when we solved equations for inverses, we flipped the x's and the y's and then we resolved. The reason I bring that up, that's exactly what happens. This part you are going to want to probably write down. That's exactly what happens when you look at the logarithmic graph. It is the inverse of an exponential graph. Okay. So instead of a y-intercept, when we flip those coordinates, it now becomes the fact that we have an x-intercept at 1, 0. The domain of the exponential function now becomes the range of the logarithmic function. And same thing, the range becomes the domain. So those flip, just like inverses do, just like we talked about. It is still increasing and continuous. We'll talk about what the graph looks like. And instead of a horizontal asymptote at y equals 0, we now have a vertical asymptote at x equals 0. Okay? And that's all because of that inverse concept, because they are inverses. Flipping the x's and the y's, and if you take a look over on the side over there, you can see the log graph right next to the exponential one. Okay? You can see those together, and we'll kind of build that where that's coming from. We'll relate those two. As some people are finishing kind of writing stuff down too, we've talked about exponential applications. We'll eventually talk about like logarithmic applications. You've done some of them. If you've taken chemistry, you've done log applications. Anybody tell me what I'm talking about? Where in chemistry do you deal with logarithms? Remember? pH. Anytime you're talking about pH, there's logarithms involved. Okay? And not something you've dealt with otherwise, but when you deal with the Richter scale, when there's earthquakes, there's logarithmic, that's an application of logarithms, is the Richter scale and measuring those and all those kind of things. So there are some applications of logarithmic functions as well. All right, let's take a look. Let's kind of compare our graphs based on the inverses. So we said exponential graph, Y-intercept at 0, 1, and we're going to look at this as like exponential growth. And we said there was a horizontal asymptote right here at y equals 0. That was our parent function graph. That's what we were working off of when we graphed exponential functions. And we shifted that 1 point, okay? We stretched things from there. We moved to the horizontal asymptote. So one of the things, remember, when you're dealing with inverses, their graphs are reflections over this line y equals x. And therefore, when you take a horizontal asymptote and you reflect it diagonally, it goes from being horizontal to now vertical. Okay? Horizontal, when you reflect it, becomes a vertical asymptote. So in this case, the asymptote now comes to here. And like we just talked about, once you flip the x's and the y's and you kind of work your way through that, if you can kind of visualize the graph being reflected over our line y equals x, that point 0, 1 gets reflected to this point 1, 0, and the graph looks something like that. What I have in blue on the screen is what we're going to work off of. That is our parent function. That's the graph that you see over on the side of the room over there. There's your parent function graph for logarithms. Okay? But I wanted you to show where it's coming from. It's coming from exponentials. And then, just like we did with exponential graphs, now we're going to add in. We've got the parent function. Now we're going to shift it, we're going to stretch it, now we're going to do the transformations and move it around, okay? Which means the vertical asymptote, we can move that left or right. We can take this graph, we can move it up, down, okay? We'll start doing all the transformations to that, okay? Which is exactly where we're headed. So again, you probably don't need to write this down because this should already be in your notes from exponentials. But just a reminder then, once we start adding in all those shifts, domain doesn't change for exponential, it's still all real numbers. The range, remember when we shifted something up or down? Okay? Well, then that means that the y values have to be bigger than whatever that shift was. Because normally it's at y equals 0. You move it up 2, therefore now y has to be greater than 2. It's got to stay above that. Same thing, that the horizontal asymptote, these two are connected to each other. Whenever you shift the graph up or down, the horizontal asymptote goes with it. Okay? So the range and the horizontal go together. And then we talked exponential-wise. We said the base. If your multiplier is bigger than 1, you've got exponential growth. If your multiplier is between 0 and 1, you've got exponential decay. Things are decaying. So just a reminder there to then relate it to where we're headed. Here's your general logarithmic equation. Okay? We still have the base. We still have a b, which we'll talk about in a second. And then we've got h and k as our horizontal and our vertical shifts. Here's what we're taking a look at. So our domain, as we move things left or right, our domain is going to shift left or right. Normally it's at x is greater than 0. It's to the right of the y-axis. But if I shift it 2 to the right, well, now x has got to be greater than 2. It's got to stay to the right of that vertical asymptote. Range is all real numbers. Just like domain was all real numbers with exponential, range is always all real numbers. The b value, we're going to focus on it, but not nearly as much as we did with exponential, because most of the time, matter of fact, I'm not even sure if there's a problem in your assignment that has b between 0 and 1. We're going to mainly focus on this right here. When the base is greater than 1, it moves up and to the right like our logarithmic graph we were just talking about. It's got that general shape as long as the base is greater than 1. It'll have that shape to it. Okay? If the base is between 0 and 1, which, like I said, is a thing. I mean, it does happen. We just aren't going to focus on it very often. Then your graph instead would move down to the right. So it would end up kind of looking like that. It almost looks like exponential decay. Okay? It's not, but it kind of looks like it. And your vertical asymptote, like I said, is at x equals whatever the shift is. We're shifting it 2 to the right, 2 to the left, whatever the whatever the shift is, that's where the asymptote is going horizontally. Okay, a lot of information to begin with. A lot of stuff going on here. Okay, this is all the information about the graph. Now let's actually kind of put it to use so you can actually see what we're talking about and see how this works. Give you a second. There's still a few people that are writing some things down. All right, let's take a look. Here's example number 1. Let's actually now, all that stuff we just talked about, let's put it to work here. By the way, quick heads up as you are writing this down. When you get to today's assignment, anytime they have you graph, I want you to ignore the directions, and this is what I want you to find, okay? The reason I bring that up, if you remember back to exponential ones, they had you make a whole bunch of T-charts. That's not how I want you to do this, okay? I want you to use the shifts and all that kind of stuff and understand what's going on with the graph versus just find a whole bunch of points and plot them. Okay, that's more of like a guess and check kind of method. I want you to understand why the graph is where it is. Okay, so this is the stuff. So any problem in the assignment today where they go through and say, graph this function, this is what I want you to do. Okay, identify the important points and then use those to do a good sketch. Okay, so first off, what's the b value here? What's my base? Base of 4. Okay, which tells me right away that this is going to be logarithmic growth, okay, which is what we've been talking about. It's kind of that graph that goes up and to the right. Okay, so we know that the shape of the graph based off of that, which, by the way, I told you, we're not going to deal with logarithmic decay very much. So almost always we're going to have bases that are bigger than 1. So they'll have that logarithmic growth. What's the value of h? Where's my horizontal shift here? 3 or negative 3? Which one? H is 3. We are going 3 to the right. Okay, we're going to take our graph and we're going to shift it 3 to the right. How about k? 0. There's nothing after the fact that's added or subtracted at the end, so there is no vertical shift. Okay, which tells me, by the way, before I even do anything else, the asymptote of a logarithmic graph is normally x equals 0. Well, because we're shifting everything 3 to the right, the asymptote is at x equals 3. Okay. So let's put it together. Let's kind of take a look at what's going on here. Don't graph this yet because I'm going to shift it in a second. I want you to see where you start. Normally, that's our x-intercept, and normally that is our vertical asymptote, and normally that's the graph that we would go off of. We're taking that entire thing and moving it 3 to the right. That's what's happening. Okay, vertical asymptote, that 1 point, the general shape of the graph isn't changing because b is bigger than 1, okay, and so on and so forth. So, if we shift all of that, that means our vertical asymptote, we said, comes to here. That x-intercept that was normally at 1 now shifts 3 to the right. It is now over at 4. We're not shifting it up or down at all, so I don't have to move that point anywhere else. And again, since the base is bigger than 1, we know we have kind of that logarithmic growth here. Let's fill in a couple more points here. First off, x-intercept on this one's pretty straightforward because we already found it. You don't have to go much further than this because what is my x-intercept? It's 4. Okay? We took it from 1 and we just shifted it over. We didn't have to move it up or down. So x-intercept is at 4, 0. Okay? By the way, again, reminder when you graph this that not a lot of people did on the exponential one. I want you to label that 1 point. Okay? There's only 1 point on the graph necessarily that I want you to label. That's the one. I want you to put on here that this now is located at 4, 0. I've actually put the ordered pair on the graph. So I don't have to worry about finding a different x-intercept because it's already there. What's the domain of this graph? From what to what? I'll give you to the infinity. Oh, excuse me. Hang on. I was thinking something else. Including 3 or not including 3? Not including 3. It's got to be bigger than 3. Okay? X has to be greater than 3. It's got to be to the right of that. So in this case, from 3 to infinity, what's the range? It's always all real numbers. It's always going to go down to negative infinity. And even though this will be a gradual curve, it will keep increasing forever and ever and ever, even though it's somewhat gradual. So this is negative infinity to infinity. Okay. And there's your first graph. There's your idea behind it. Using the shifts, identifying what it tells you. Okay, that's what we're looking for. Any questions? Anything not make sense yet? Okay, let's do another one together then. And then I'm going to give you one to practice on your own. All right, let's start at the beginning. What's the base? 2, which tells me, again, I've got logarithmic growth. Okay, it tells me the shape of the graph. What's the value of h? How far are we shifting this horizontally? Again, it turns out it's 3 to the right. Okay, and up or down? Up. We're going up 1. Okay, so again, right away, even before I go to the graph, I'm going to kind of identify the asymptote. Normally it's at x equals 0, but we shifted it 3 to the right. So now it's at x equals 3. Okay. Once again, let's kind of sketch in the graph, and then we'll come back and finish this other stuff once you kind of see what the graph is looking like. Normally our point is at 1, but we are going to shift that 3 to the right and 1 up. So we'll be over at 4, 1. And again, label that point, okay? So that I know that you shifted it correctly to the right spot. Vertical asymptote, shifts from 0 over here to 3. And then because our base is bigger than 1, like I said, we kind of have that logarithmic growth. We can sketch the graph in from there. Something like that. Let's fill in the quicker ones, and then we'll come back to the X-intercept and add one more point to our graph. What's the domain of this one? 3 to infinity again, okay? Greater than 3. So domain is from 3 to infinity. Range? All real numbers, always. Negative infinity to positive infinity. All right, so we've got those filled in. Now, here's the part that's a little bit different. This time I don't have the X-intercept because there was a vertical shift. So that point that we shifted is no longer on the x-axis. So an X-intercept is when what is true? When y equals 0. So here's what we need to do, and this is a new part, okay? We're going to take this equation, and I'm going to set it equal to 0, and we got to find x. We're going to solve. Okay. So I'm just going to do it right here. Log base 2 of x minus 3 plus 1. We're going to set that equal to 0. And we're going to try to figure out what's the x value that gives me 0. In order to do this, it's only a couple of steps. Step number 1 is I want to get the log part by itself, which means I'm going to subtract the 1 to the other side. Okay? I want to get the logarithm by itself. So we're going to write this as log base 2 of x minus 3 equal to negative 1. Now we're going to go back to what we did yesterday. Now I want to use, it's still pretty difficult to kind of figure out what x equals, but we can make it simpler by using our definition of a logarithm and changing it into exponential form. Yesterday, remember we went back and forth between exponential form and logarithmic form? Well, right now I'm in logarithmic form. I want to switch it back. Okay? So if you remember what we did yesterday, we start with the base. 2 raised to what power? The negative 1. Remember, the logarithm is always equal to the exponent. That's what a logarithm is finding. So 2 to the negative first power equals the argument. In this case, x minus 3. Okay. So you took your logarithmic equation and you rewrote it in exponential form, just using the definition. Okay. Just like we were doing yesterday. Now let's go a little bit further. What is 2 to the negative 1? Not negative 1/2, just 1/2. Okay? 2 to the negative first power, remember a negative exponent drops it to the denominator. So this is really just 1/2 equals x minus 3. And now we can just add the 3 over. X-intercept is 3.5. Okay? So there's a little bit of work in order to find the X-intercept. A little bit of work going on that one. And if you take a look at the graph, by the way, if we sketched it fairly accurately, we actually did a pretty good job here of, there's the 3.5 right there. Okay? Turns out that it looks like it's right on the curve that we came up with. That's really the one extra thing that you're going to have to try to find, is that X-intercept. Set it equal to 0, get the log by itself, and then go to exponential form. Okay. All right, let me give you a practice problem here. Let me give you a chance to try this on your own where I'm not directing you. Okay? Here you go. Try this one. There's your logarithmic equation. Identify the features, and then, like I said, graph them. Find the X-intercept again. And I'll just walk around, and if you have a question or you get stuck on something, just let me know. But I'll give you a few minutes here to try to put this together. You're almost there. You almost maxed it out.
I almost finished my lab in physics.
Great.
I did something in physics.
That's good. That's good. The hardest part will be to try to find that X-Intercept. Trying to set that up and solve for that, since we haven't done a lot of that yet. All right, let's check. Let's see where you're at. Let's see how you're doing. So if we start identifying different parts, base of my logarithm is 3, which tells me we've got logarithmic growth. Okay. Horizontal shift, we're going to go 2 to the left and down 5, which means if we're going 2 to the left, that's where your asymptote is located at x equals -2. Okay. And now we can start putting things together. Okay. So in this case, let's put x equals -2. Let's put our asymptote in there. Then remember, the point that we're shifting is normally your x-intercept at +1. Okay? Normally it's that point right there. But we need to shift that according to h and k. So we're going to take that point and go 2 to the left and down 5, which means this point is going there and then down here. 2, 3, 4, 5 to right there. Okay, that's where that point is going to be located. Again, label the point. Okay, -1, -5 is where you ended up. Okay. And we know that, again, because our base is 3, we've got that logarithmic growth. So it's going to look something like that. What we don't have yet is the x-intercept. I'm not quite sure yet where this is going to cross. It will cross, we just don't know where. Okay? Real quickly, what's the domain?
-2.
Yep. From -2 to infinity. Okay? By the way, quick heads up on that one as well, just to confirm the second part of it. You might be just working off of the graph, but remember what we said about logarithms yesterday? You can't take the log of a negative number. That's why x has to be bigger than -2. -2, -1, 0, so that you end up with a positive answer right here. That's all when you look at the equation, that's all you're doing. So the graph is, yeah, it's to the right of -2, but it's also coming from the equation that I would say x plus 2 has to be greater than 0, solve for x. So you can do it algebraically as well. Range, we talked about, that's always -infinity to infinity. All right, and here comes the part that, like I said, is probably the most difficult part. Let's set this equal to 0. Let's work our way through. Okay? Log base 3, x plus 2, minus 5. We set it equal to 0. What's step number 1? Add the 5. We got to get the log by itself. Okay? And I know, so the -5, we got to get rid of that. So I'm going to add that to the other side. Log base 3 of x plus 2 equals 5. Once the log is by itself, we need to now use our definition of logarithms. We need to change this to exponential form. You always start in the same spot. Base. 3 raised to what power? Our log always equals the power. 3 to the 5th equals whatever's in the argument then. Okay? Always comes back to the argument, x plus 2. And now this actually turns out that it's a whole lot easier to solve at this point. 3 to the 5th power is what? 243. Yep. Equal to x plus 2. You subtract the 2 over, and it turns out that our x-intercept is 241. Okay? 241, comma, 0. Which, I told you it would get there eventually, but it's going to be way down the line. It's going to be way down at 241 where it crosses the x-axis. Okay? Yeah?
So do we have to worry about a Y-intercept too or no?
No, I'm not going to worry about that too much. By the way, if you did, since it's a good question, if I did right now, if I asked you to find the Y-intercept, what would you do? Yeah, just put 0 in for x and get an answer. Yeah, so that one's not as big a deal because that's more like a calculator type problem. Plug in 0, see what you get for an answer. Okay, so if you had to, that's what you would do. Okay, number one concept is this today. Most of the problems you're going to be looking at, you're going to be doing these types of problems or at least describing them. Again, as you're doing it, this is what I want you to find. Okay, I want you to identify these points. I want you to graph it. Make sure you label the one point that gets shifted. There are a few other problems. Let me just refresh your memory here for a second. Okay, this will be quick because this was yesterday. No, don't refresh your memory. Reminder, and I don't even know that you need to write this down other than just pay attention and just quick review. Reminder that natural logs is really just log base e, okay? Rather than base 2, base 3, base 5. Log base e is what's called a natural log. And the only part that I'm coming up here, this is why I said you don't really have to write these down unless you want to. These are the same 4 properties we talked about yesterday. Exactly the same, except now dealing with natural logs. Natural log of 1 equals 0. Why? Because remember, the base is e. E to the 0 power gives you 1. Natural log of e is 1. Why? Because when the base is e, e to the first power gives you e. Okay? The point I'm trying to make here is these are the exact same properties as what you had yesterday with regular logs. Natural logs and regular logs have the exact same properties. They work the same way. It's just a different base. Okay? That's why I said I don't even think you necessarily need to write these down. Let's see if you can do a few of these in your head here. Here we go back to the no calculator like we did in the warm-up. But now dealing with natural log ones.
-1.
Very good. First one is -1. Reason being, if you think about what this is actually asking you, this is saying e to what power gives me 1 over e. Just like in the warm-up, that means that power is the negative first power. How about number 2? This one should be quick, hopefully. It's just a property. Yep. There it is, right there. Number 3 should be quick. What is it? 0. There it is, right there. And number 4 is a little bit like what we did in number 41. What's the answer to this one? It is 2. Because natural log of e is 1 times the 2 that's out front. So the answer is 2. Last question I have for you, and I'm not going to do this. Evaluate with a calculator. You can plug that stuff into your calculator. Which one of these has no solution? Yeah. Just a reminder that even with natural logs, you still, there's your no solution symbol, you still can't take the log of a negative number. Okay? E to some power will never equal 1. Okay? It's not going to happen. All right. There it is. Pages 203 and 204. Again, it looks like the assignment looks a little bit longer in terms of number of problems. It is. But a lot of these are fairly quick ones. Some of them are just like what we just did. just evaluate or just describe something. So even though there's more problems, hopefully it's not a whole lot more time, okay?